Our next speaker is Sumit from Columbia. He will talk about motif counting via subgraph sampling.
Thanks, Christian. I'd like to begin by thanking the organizers for the invitation and also for a wonderful conference so far. So the talk that I'm going to give today is joint work with Bhashar and also Shayan Das, who's a PhD student at Columbia. So let's try and jump right in. So the talk will roughly have 5 parts. I'll first explain the question that we want to study, and then I'll try and motivate the answers that we find. And then I'll use some examples of graph ensembles to illustrate the results. Depending on the amount of time left, I'll give a very high level proof overview and then conclude. Okay, so what is the question that we want to study? So no graphons here. Graphons will make a very brief appearance in one slide later on. So you just have a sequence of graphs, but let's say you have one large graph, which is level, whose vertex set is 1, 2 up to VGN, whose edge set is EGN. And that's your parameter of interest, or that's sort of, you don't know this graph, right? This is a big graph, you don't know this, you don't see this. And so, and H is a connected graph of fixed size, you know, think of the usual candidates. H is an edge or a triangle or any motif that you like, stars, cliques. H does not change with n. And I'll assume H is connected. The story should remain the same if H is not connected. Okay, so let NHGN denote the number of copies of H in GN. By copies, I do not mean induced, so the number of injective homomorphisms. And so that's what NHGN is. And this is our parameter of interest. We want to understand what this number is. And so, okay, so since we do not see this graph, we need to see something. And so what we are going to see is a random subgraph of this big graph, right? And so, okay, so let's try to explain the sampling mechanism for this talk. So it's going to be a very simple sampling mechanism for each person in your network or for each node in your graph. Decide whether you want to keep that person in your sample or not. So with probability Pn, which is again allowed to change with n, and ideally I'm thinking of Pn sparse, right? So I'm thinking, okay, this all of this allows. All of this works for Pn equal to P fixed as well, but you know, the interesting case is when the Pn sparse. So okay, so you know, you decide whether that vertex enter your sample or not, and then when you decide which vertices enter your sample, you just take the induced graph on those vertices. So you have a big graph, you choose a bunch of vertices by this, and then just look at the edges between them. So that's your sample graph. That's it. So by choice, your sample graph is a subgraph of your big graph. And you know, the name proposed by people who have looked at this, so we did not propose this model, is a subgraph sampling model, because as I said, your sample graph is a subgraph of the big graph, and the number of vertices in your sample graph is clearly random. It is a binomial distribution, all very good. And so, okay, so let's try and come up with a reasonable estimator, and I guess you know, this seems to be the most natural estimator that one would come up with. So let's try and motivate the estimator. So let's see if you have a particular copy of H, let's say a triangle, you know, 1, n, and n minus 2. You want that copy to be retained in your sample. So you need to pay for each vertex to enter your sample. So you're going to pay PQ. So in general, you're going to pay P to the number of vertices for each copy to enter your sample. So, you know, if you denote by NHGN, which is the number of copies of H in your sample graph GN, then this expectation is just P to the V times the number of copies in the big graph. And this gives you your natural estimator, just divide, right? That's it. Okay. So one comment is that this talk assumes that we know P throughout. So you know the sampling probability. If you don't, what we can do, is if you know the number of vertices in your big graph, you can just estimate Pn by the number of vertices in a sample by the number of vertices in big graph, and the resulting confidence intervals will only change by a constant. So I'm not going to talk about that here, but you know, if you don't know the number of vertices in the big graph, then that's a different story. So that's, you know, if you do know the number of vertices in a big graph, knowing and not knowing Pn is not too much of a difference. Okay, so you know, it was shown in this paper by Jason Klusowski and Yuhong Wu that, you know, this natural estimator is minimax rate optimal among the class of all boundary graphs where the bound is of course free of n. The question that we are going to take is we are going to take the same estimator. So one comment is that they consider induced copies, and here we are going to not consider induced copies. Of course, you know, you can write one in terms of the other as a inclusion exclusion formula. But so the question that we want to study for this talk is sort of the more classical statistical questions of consistency and asymptotic distribution. So that's the question that we want to study. So therefore, in our minds, we have a sequence of graphs Gn and Pn, and as such, there is no assumption as how you get Gn. You could get it from a graphon model, you could not. That's fine. So of course, we need some assumptions. Like, okay, you will see the assumptions coming in, but you know, as such, there is no, your Gns are not random. Yes.
Are you assuming that your graphs are dense though?
No. Gn is not dense. So Gn is just a sequence of graphs.
But that it could very well be that n is just 0.
Yeah, that's possible. Will, of course, in that case, estimation would not be possible.
I'm sorry?
So if this is, so our next slide will rule out the case that is 0. So this estimator is always defined. Doesn't mean that it will do well. Okay. Right? So now we'll characterize precisely when it will do well. Right. So but to define this estimator, we can always do it. Right.
So I have a related question. So in the result of Wu and Klusowski, I'm slightly astonished that this works in the bounded degree setting, because again, this number could actually go easily to 0 or something. I mean, right? Because you may not say it may contain many copies of a certain graph, which you just don't see by this random sampling.
Right. So the point is that if it is 0, then no estimator will do better. Right. So if this estimator is minimax at optimal, meaning in the settings where
wait, it's min-max optimal under that sampling scheme.
Under the sampling scheme. Yes.
Because you might have a different sampling scheme which sort of has same complexity, which gives you the correct count.
I fully agree with you. So you fix the sampling scheme. So throughout the talk, we'll use this vertex sampling scheme.
So when they say min-max optimum, that means for fixed Pn, and so
for fixed Pn, if you look at if your Gn is among the class of all boundary graphs bounded by some constant, in that class, this estimator is minimax at optimum.
I see. So what they're saying is, if I sort of have this sampling scheme, I get as input the induced little GNs.
Right.
Any estimator which uses that as an input,
yes,
just counting is min-max
optimal,
and makes a lot of sense. They will look at induced graphs, because if you are, since this allows sparse setting, induced graphs behave slightly better in the sparse setting than subgraphs.
Right. And sort of the point is, so one thing which I wanted to sort of point out in the middle of your question is, it is perfectly possible and that there is a different sampling scheme which does much better if you want to count, let's say, motifs, right? And so, for example, if your big graph G has varying edge density, for example, if you know that there is a hub here somewhere, then ideally I would use more sampling power there. And if there is a less edges somewhere, ideally I use less sampling power there. But this means that I know something more about the big graph Gn, which is not sort of part of our modeling assumption. So right now we are fully agnostic about the Gn, big graph Gn, and this is the sampling scheme.
Yeah, there would still be many possible other sampling scheme, like choose k random points and choose the balls of radius k around them.
You're right, and I agree that if you make the sampling scheme different, other estimators could be more natural. That's perfectly plausible. Other questions about the model or the sampling scheme? Right. Okay. So what we want to understand is, when is this consistent? If you have a sequence of graphs G and Pn, and when is this asymptotic normal? Okay. We don't know that. What is the asymptotic distribution of this? So I put the word consistency in quotes because, of course, we need to make some sense of it. because typically, at least when you say something is consistent in statistics, we have a sequence of estimators trying to estimate a real number. The difference, needs to go to 0. However, as you might guess, the type of examples that we look at, the number of copies of H in Gn will be large. And so, of course, you don't want the difference goes to 0, because that means they have to be exactly equal, which is a bit too much. So we demand the most natural thing, we demand ratio consistency, right? So, and here we sort of throughout, we will assume that the number of copies of H in Gn is greater than or equal to 1. Otherwise, I don't even know how to make sense of this. So throughout, we'll assume that there is at least one copy of H in Gn. And just to give you an insight, this will never be consistent if this doesn't go to infinity. So you can only, this will come later. But at this point, this will be an assumption throughout. So this is what consistency will be for us, the ratio going to 1. Yes.
I'm a little bit confused. Maybe it's very natural to think of this in the limit, but I have no idea how this changes with n. So your graph is, you said you're agnostic about the big graph, fine, but
Yes.
and you're keeping the sampling scheme, but you're adding PU for every new vertex U as
No.
PN
is no. So
yeah.
when you give me the graph at the nth level, so think of n. So for us, suppose n is 100, and suppose you observe the graph on 100 vertices, and suppose you decide your sampling probability Pn is 0.03. That's it. So for fixed n, for all the edges, I use the same p.
And then when for n plus 1?
For n plus 1, I use Pn plus 1, a different p. So, but basically, think of the statistical question where you are usually given x1, x2, xn from some distribution. You are not given the whole sequence, right? So you will only be given Gn, Pn for some n. But all I'm saying is that there is an underlying Gn, Pn which you could have been given. So there's an underlying x1, x2, xn, or you could have been given x1, x2, xn plus 1.
I think it's still a little bit subtle, but okay. I can go with this.
So I think one point is, I think what you're trying to ask is how is Gn plus 1 operate from Gn? Right. The answer is no restrictions. You can build it in any way you want.
So no consistency.
Sorry? No consistency. No, exactly. So no consistency in a different sense. No consistency of law. If you're thinking of, so if you have Gn ij, the edge is present, Gn plus 1 may or may not. So it's perfectly okay to build it in a consistent way. Nothing will change. That's the point. This will not impact anything that I'm doing. Okay. So let's see an example. I think this will this may answer some questions. So suppose Gn is a line graph on n vertices with n minus 1 edges. So you have a big line. So this is what I mean Gn changing with n, right? So this is the Gn. And so suppose H is a path of length 2. This is just that's it. So 3 vertices, 2 edges. So you want to count the number of copies of H in Gn. So essentially the number is n minus 2, right? I mean 1, 2, 3, 2, 3, 4, 3, 4, 5, and so on. So you sort of have a moving window, and you get this number n minus 2, which is basically n for all practical purposes. And so okay, now so we have some sample probability Pn, and this is where this is the Pn part. And so what will be your Gn? Well, if you choose just one vertex and don't choose your neighbors, it will be an isolated vertex. If you choose 2 consecutively on edge, if you choose 3 consecutively, path of length 2, path of length 3, and so on. So basically your sample graph will be a disjoint union of paths of varying lengths, depending on which ones are possible and which ones are not. So that will be your sample graph. And so how many paths of length 2 will you see? If you take the expectation, well, you get np cube many paths of length 2, because you want to select all the 3 vertices, you have to pay pq for that. Now, of course, you can do this concentration only when this goes to infinity, but this is the expected number. And if it goes to infinity, this is the right number of paths of length 2 that you will see. Now, if you have h tilde, which is a path of length 3, then you're going to see np to the 4 many copies of that. So there's a reason for including h tilde, even though I want to count h. So, okay, so suppose Pn is such that the first number goes to infinity and the second number goes to 0. So essentially, you are saying that there are no paths of length 3, and there are lots of paths of length 2, and of course there are paths of length 1, and there are isolated vertices. So there are also those. So your sample graph is a disjoint union of paths of length 0, 1, and 2 with high probability. That's your sample graph. So you're a big graph, this is a sample graph. And so, okay, so your estimator is this. And so with high probability, this will be np cube over p cube. And if this goes to infinity, and this will be n, which is sort of close. So in this setting, it is actually consistent. So this is what I mean by, so Pn changing with n. So I hope this answers some of the questions that we had. Right. So this is and as such, I did not put any assumptions with Pn other than this is sort of the assumption that I put here, and I'll try to we'll be precise about exactly what we need for consistency. But this is just a dummy example. Yes.
Why do you need the n times Pn to the power 4 to go to 0?
Just to give you a structure of just to be able to write this line. Otherwise, you'll also have disjoint union of paths of length 3. That's true. No. This is just to give you a nice, so just to give you a description. That's it.
Okay. Yeah, and the expected value is going to be much more.
Yeah, I'm not claiming that
changes, right?
exactly. I'm not claiming that I need this for consistency.
Okay.
This is just an example to say how the sample graph looks like, and then say that in this case your estimator is consistent. Okay, so the point is that your sample graph Gn depends on your perspective, but doesn't look like your big graph, but it's still consistent with very small p, right? You don't need p to be fixed here. P can go to 0 at reasonable rates. Okay. So the normal, the asymptotic distribution part is more standard, but let me still just say what is the question we want to study. So this is our estimator. You center and scale it the usual way. This is same as studying the number of copies of H in your sample graph, centered and scaled. Okay. As one might guess, maybe it's Gaussian. However, as it turns out, and this I'll sort of go briefly over in the example in the later part of the talk. I hope I have some time for that. This does not hold here in the sense that it's possible for your estimator to be consistent, but these fluctuations to be non-trivial and non-Gaussian. In the example, it will be a centered Poisson, and in particular, the class of limits could be a Gaussian and a Poisson and a mixture of this, and we don't know the class of all possible limits, and that's. But okay, so the modified question that we propose for the talk, which we will answer, is that can we say exactly when it converges to normal 0, 1? So ideally not a sufficient condition, but if and only if when can we estimate the normal distribution to find out confidence intervals for this quantity. So these are the questions that we want to study in this talk. Right. So that's the setup of the talk. So now let's try and answer them. So I'll first explain why we anticipate the answers that we do. So let's ask the consistency question, right? There was this dummy example where things were consistent and nice, and all the moment calculations worked through. So in general, it's not always consistent, and it's not hard to think of what could go wrong. You take Gn to be an n star. So here the number of vertices is actually n plus 1, but that doesn't matter. You could take any growing sequence and things are fine. H is an edge, and your sampling probability Pn is a half. And you can also give examples with Pn going to 0. So okay, so there's a hand-drawn picture. Your Kn here n is 5, and there are two possibilities essentially, right? Either you get to choose this central vertex or you don't. Now, if you don't choose your central vertex, what you're going to see is just a bunch of isolated vertices here, right? Just a bunch of leaves here. And in this case, your number of edges in the sample graph will be exactly 0. That's it. On the other hand, if you happen to choose your central vertex, which happens with probability half, then you essentially what you see is a star graph, right? I mean, what you see is a smaller star graph. And then the number of edges is a binomial n half, right? I mean, the number of leaves that you choose. So these are the two possibilities. So let's try and write them down. So with probability half, you see a bunch of isolated vertices. So in this case, your estimator is exactly 0. There's nothing going on. with probability half, you choose the central vertex, then your sample graph is a star graph with binomial many vertices. In this case, the estimator is 4 times xn. You get the 4 because of the half square, right? You have the half square scaling, so that gives you the 4. So your estimator n hat is 0 with probability half and 4 times xn with probability half. If you take if you take limits, you will get 0 with probability half and 2 with probability half. So in this example, for this sequence of graphs, this nice estimator is not consistent, but it's yes.
Well, I mean, the brief answer could also be playing devil's advocate that you should not do sampling for a star, right? Subsampling.
That would be the answer. Yes, you're right, and the answer
it's
is
too sparse. It's not sufficiently well connected, and you can destroy the entire graph by
not
removing
sparse.
just one vortex.
Some people are not supposed to be much more popular than others.
Precisely. It's not robust in that setting. Exactly.
It's not robust in setting, and that is what we will make precise. Yes, you're right. Because in this setting, to make it work, you sort of have to know that there is this popular guy and other. I don't know of natural sampling schemes which will work here. But okay, that's, I mean, of course, natural is within quotes here. Okay, so as Remco pointed out, big is compared to the others. Big is not just within yourself. Big is compared to relative to the graph. Big degree vertices are not good for you. So okay. So presence of big degree vertices is going to, in your sample, is going to boost up your estimate too much. Absence will sort of reduce it to too low. And it's essentially what you want is to have the number of big degree contributions. The contribution of the, I mean, we don't want to remove the big degrees entirely, but we want to ensure that the big degree contribution is low. And the precise characterization for the edge case will sort of answer the more general case of the theorem. But let's first start with the edge case. If you sum over the degrees which are large, and large is exactly this threshold, and you divide by the total number of edges, that has to go to 0 for every epsilon thing. So this is the first question.
Is this related to some form of uniform integrability?
Maybe that's a good. So essentially what we do is we truncate the graph and we sort of do a second moment argument on the truncated graph. So,
but you're saying that it's exactly equal to 0, not that it vanishes or very.
Oh, there's a limit. There's a limit. Sorry, that's a typo. There's a limit.
Okay. There is a limit. Okay.
My bad. There is a limit.
That's closer to
no. That's a big difference. So I cannot write there, but there's a limit of it. Right. Yes.
Yeah, so when you're estimating,
I think you need the mic. Sorry.
For the estimation of just the ages, if you have sampled the ages instead of the vertices, then you always get the consistent estimation, right?
For very sparse, I mean, okay, that's a question that we are trying to study now. I am not sure about the answer, so let's talk about that offline. Okay. That's work in progress. Yes, there's a question.
For this condition, apparently you don't know anything about the graph GN, right?
Right.
Then how do you know whether this condition?
So I mean, it's a general thing, right? You can only, so the conditions for consistency usually depends on the unknown parameters. That's in general, ubiquitous to statistics.
So for your problem you started with, you don't know anything about the
right, right. And so I'll give you sufficient conditions later, which you can check again by plugging in estimates. But these are stairway to inference, right? I mean, suppose you want to estimate the mean in a normal family. The bounds are given by the variance. You now need to estimate the variance. And now the bounds of the variance will have some other parameters involved, right? It's the usual stairway of inference problems. You can never stop this. At some stage, you have to decide, okay, that's that. So, but you can continue this. So I'll tell you how to check this condition, right? But again, checking this condition will assume something more. So it's not, this will not be blanket, right? Okay, and also the expected number of copies of edges have to go to infinity. This is sort of the equivalent of saying the sample size goes to infinity. So this sort of says that, if this is too small, like 5 or 6, this is not going to work, right? So you need enough number of edges in the big graph and enough being quantified by this p square. And this is not a sufficient criteria. This is an exact criteria. This is an if and only. So if this doesn't hold, your estimator will fail. That's it, period. Right? So that's what's going on for edges. So let's now state the first result, which is our first main result. is what's going on for H's, general H's. The same story holds. I mean, you want to estimate this number of copies of H in Gn. What we need to control are groups of vertices which contributes too many copies of H, right? That's what's going to mess up your estimator. So let's define the analog of degrees in this context. Suppose you have a set A of vertices in VGN whose size is less than V of H. Then let TH of A denote the number of copies of H passing through A, right? So I'll give it.
What does that mean?
Passing through means the number of injective homomorphisms such that, so for the triangle case, let me write it down.
Does it mean the vertex set has non-zero intersection, or does it mean it's contained?
Not contained. So let's see. So let's see. Suppose H is a triangle, then TH of 1, 3 is the sum over I, A1I, A3I. So it's a number of so 1 and 3 are given to you. It's the number of triangles passing through. It's a number of triangles like this. Number of triangles that contain the H1.
So it is a number of. It is a number of H whose vertex set contains A.
Right. And okay, so the same story holds. So now there is a limit, so that's good. Your estimator is consistent if and only for every epsilon. This sum, you now have to sum over all sides of A starting from 1 all the way up to VH. Then this TH indicator, this truncation point, this is small compared to the total number of copies of H in Gn. The next slide parses this for the H condition and convinces you that this is exactly what we obtained for the H case. But yes.
For this passing through A, you only need nodes so here you said edge 1 and 3 present in the triangle, or
right. So A is a subset of nodes, and so then TH of A.
You don't want the induced graph of A to be present.
No,
okay,
no,
just the nodes.
Right. Okay, so let's try and explain why this gives you exactly what we got in the H case. Now, the way to get the H case is to consider sizes of A, which is 1 and 2 separately. That's it. That will give you the two conditions, right? So because for the H case, VH is 2. And so, okay, cardinality is 1 or 2. And therefore, if you look at size of A of degree, if you look at size A sets A of size 1, then TH of A is exactly the degree. So you get back this condition again with a limit which is missing. So I apologize for that. On the other hand, if you look at sizes A or A is of size 2, then basically you get the indicator. So you're summing over indicator age bigger than this cutoff. This has to, the limit has to go to 0. Now this doesn't exactly look like it, but a moment's thought shows that this is exactly same as this. Why? If this is going to infinity, then for every epsilon fixed, this will go to infinity. So this will never happen, and this is 0. On the other hand, if this is bounded, then for epsilon small enough, this will be 1. So this whole thing will be 2. So, this criteria is just more conveniently written like this. But in general, that's what it is. Right. So, okay. Let's try to answer that. Yes.
In generalization criteria contains the fact that the expected number of copies. It's true in general that your criteria contains the fact that the expected number of copies tend to infinity.
Yes.
Yes.
Yeah. That's right. You need that. That's all. That always follows from taking A, which is the maximum size. Right. The way to get that would be taking A to be the VH. Exactly. So okay. So asymptotic distributions. So we center and scale. We want to know the limit of this. And as I tried to indicate, this may not have a Gaussian limit, even though your estimator is consistent. Let's try to go briefly over the example. This example is sort of course, we needed some time to come up with the example. So let's try to explain what this example is doing. You have log n many n stars and log n many cliques, and the size of the cliques is n to the 7/12. Of course, these were carefully chosen. And so this is your big graph, and you see parts with varying edge density. Of course, that's allowed. And okay, so you choose your vertices, you choose your samples. So your samples can come from here. And so here the red, okay, the color is, okay, I guess visible. The red ones are the central vertices of the stars that you choose. The green ones are the leaves that you choose. And Y represents the number that you choose from here. So Y is a binomial, X is a Bernoulli here, depending on just indicating whether you choose that one or not. And the Z's represent the number of things that you choose per click. So Z is also a binomial. So this is a big graph, and a particular relation of choice of samples is indicated by the colors. And so what is the number of edges? So I'm estimating number of edges, just to be clear. So the number of edges is, you have to choose this one that accounts for the xi. Then you multiply by how many of the yi's you choose, so xi, yi, plus per click you get zi choose 2. So where xi is a Bernoulli, yi is a binomial np, zi is a binomial n to the 7/12. So you can write very explicitly the number of edges that come in your sample. So it's not I mean, this is a very nice, okay, I mean random variable, you can analyze it to death. Okay, so as I indicated in the last slide, you have log n many stars and log n many cliques. And how many vertices do you have? So log n times per star you have n many vertices, and per click you have n to the 7 many vertices. So this one dominates, so n log n many vertices, and per you have this factor log n, per star you have n many edges, but you have this becomes quadratic now, and this one dominates for the edge one, so n to the 7/6 log n many edges. So for the vertex one, the star parts dominate. For the edge part, the cliques part dominate. And so okay, so as I wrote in the last slide, this is the exact representation for the number of monochromatic edges. So xi is a Bernoulli, yi is a binomial, zi is a different binomial. So this is just what I had in the last slide, just written more cleanly. And so let's try and check the consistency. I'll gloss over the limit distribution part, but that's in our paper. So we choose P to be 1/log. And so this is the exact condition, again with a limit. There's other condition, but that one also, that's easier to check. So what is the number of edges? From the computation that we did, this is n to the 7/6 times log, and P is 1/log, which cancels this. So you get n to the 7/6, right? So number of edges times P, this is your threshold actually, is n to the 7/6. Yes.
1 over the number of edges should be 1/Pn times the number of edges, right?
1 over the number of edges. This should always be the number of edges here. The threshold has P. This one does not have P. Okay, so this one has nk to gn here, right? Only the threshold has a P. Okay, so the threshold that you need to compare here is n to the 7/6, but that's great because this is your truncation point, but you don't need to truncate at all because the star graph have maximum degree n, and the cliques have maximum degree n to the 7/12, which is much less than n. So this is 0 for all, for every fixed fixed for all n large enough. This quantity is exactly 0, and therefore it's consistent. You cannot check this by a direct second moment argument, but it shows that a truncation will work, and that's actually what our theorem does as well. And then so consistency holds. The limit is a centered Poisson. Let me gloss over that fact because it sort of involves more computation with that formula, but it's not too bad at all. Okay, that's the limit. So in general, the question is
limit of what was the Poisson?
Limit of the number of. So you take the number of edges in your sample graph, subtract its expectation, divide by square root of the variance. So you do the thing which is supposed to take you to normal, and it ends up in a centered Poisson. Centered part is fine because your things at mean 0, so the limit should have mean 0. That part is fine, but the Poisson part is surprising.
Yeah, because I was just surprised because if you scale by the variance,
Square root of the variance.
you still end up getting something that's integer valued or almost integer valued, which seems surprising. Maybe I'm just missing something.
So maybe we can go over the computations.
Sure,
right,
sure.
right.
Yeah,
Sure,
thanks.
sure, sure. Okay. So there are two ways.
And where did the z's go?
Where do the z's
Are
go?
the z's so well concentrated that they vanish in the distribution?
So the z's, I think the fluctuations of z's are of smaller order. Right. So z contributes more to the mean, but less to the variance. The fluctuations of z's. So right. So that I think is the answer to Shankar's question. I was trying to remember as I was answering. The fluctuations of the z's are of lesser order. So essentially, it's just the first part which contributes to the answer, and that's why you get an integer value random variable. So z's only contribute exactly. Sorry.
So the z's make sure that you're consistent.
Exactly.
But they don't contribute to the fluctuations.
Exactly.
Ah, I see.
Right. That's how the p's were chosen to make our life easy. So okay. So what could we do? Well, so one question which I still find interesting, which we don't know, I think currently how to do, is characterize a class of all possible limits when your estimate is consistent. Okay, so that's that. The other one is, can we say when is this exactly Gaussian? And that's something which we'll try and answer in the next two results. So, and how much time do you have left?
5 minutes.
5 minutes? Oh, okay. I should go a bit faster. I see. Okay. So okay, let me try. Let me go over the result, and then I'll go over some examples as well. If okay, so if p is less than 1/20, pn, so it's a sequence upper bounded by this number, then the Wasserstein distance between the center random variable normal 0, 1 is bounded by a constant times the fourth moment minus 3. So that's the second main result. And as you can guess, this is an application of Stein's method of dependency graphs. You cannot directly use the theorem. You sort of have to go into the bounds and tweak it a bit, but that's fine. And this sort of tells you that whenever the fourth moment goes to 3, if p is less than 1/20, your random variable goes to normal 0, 1. So that's that. So of course, in that example, the fourth moment doesn't go to 3, but that's okay. So this is an example of a fourth moment phenomena. And of course, there are lots of examples of this. As far as we know, the first example was discovered in this paper by Noalat and Picati. But by now, there's a lot of, for more examples, you can see Ivan wrote this web page where dedicated to just connecting examples of fourth moment phenomena. So there's many examples where, you have linear, multilinear form of random variables and such a fourth moment thing happens. So let me just go over some quick comments. You do need some, so the upper bound p and less than 1/20 is not an artifact. You do need some bound on p for this fourth moment to hold. We have another counter example, again built of stars and cliques of different sizes, where pn is p, which is fixed, which is larger than 1/20, fourth moment goes to 3, the limit is not Gaussian. If I remember correctly, there is no limit. But okay. Also, the
so it's a counter example for arbitrary pn small. So what if pn is sort of 1/18? Or do you have an example for
no. So the counterexample is very sensitive. There's a polynomial which we want to vanish. So the counterexample that works for the specific p will not work for even if you change p plus minus epsilon. And what we think is that it will only break down at countably many p's.
But are the countable many p's it breaks down? Do they have an accumulation point at 1/20?
We don't know that. We do. So we have one counterexample at a fixed p, and we know that for p small enough, things are fine.
I see, but you don't know what the critical p is.
Right. That we do not know. That's yeah. So let me take further questions at the end. Sorry. Okay. Also, the fourth moment condition is only sufficient. In particular, we have examples where this goes to normal, and also p goes to 0, the fourth moment doesn't go to 3. So that's also possible. And so I promised you an if and only if criteria. Let me just state that quickly, and then I'll stop. So the exact, okay, I guess it's a bit notationally messy, but let's quickly go over that. Or maybe let's skip this and just state the result. So we have a truncated version of the count. So this, let me not explain what the truncated version of the count is because it will take more than 5 minutes. But we have a truncated version of the count, not the actual count. If the truncated version of the count, the second moment goes to 1 and the fourth moment goes to 3, This is if and only if your original interval goes to a normal. So there is a characterization of exact normality that is in terms of a truncated fourth moment phenomenon, where the truncation is essentially you count the number of all good copies in your sample. Good means that a copy of a triangle is good if all of its subsets are good, meaning that there are not too many triangles passing through this pair, not too many triangles passing through this pair, not too many triangles passing through this pair. There are not too many triangles passing through this vertex, and this vertex, and so on. So there's an exact, so the exact condition of good is here. It's a different cutoff than the last one, but I'm happy to talk about that if there are questions. But this is the exact if and only if result. And I guess I'm almost out of time.
Wait, I have a question on your theorem. Can you put the theorem? Does the theorem says if there exists an M, or what does it? Because M seems.
Yes. So theorem says that the double.
Oh, there's a limit.
There's a limit over M. So this time I did not forget to put the limit. So there is a limit over M. So the double limit second moment has to go to 1 and the fourth moment. So this means that lim sup has to be 1 and limit, right? In the sense of double. Okay, so let me quickly, I guess, this sort of, okay, this, let me just go over some examples rather than explaining the simulation. So for dense graphs, which is the main focus of this, this workshop, the picture is actually very easy. Suppose G is a sequence of dense graphs converging cut metric to a graph on W with this density positive. Essentially, all that we care about is this has n square many edges and n to the VH many copies of VH. That's all we care about. We don't actually care that it has a limit. Then the result is actually very simple. I mean, you have to manipulate our sufficient conditions a bit to get this, but the exact result is NP goes to infinity. So if NP is bounded, your estimator is neither consistent nor normal. On the other hand, if NP goes to infinity, the estimator is both consistent and normal. So the exact an exact characterization of normality here. We give yes.
Here you don't need P upper bounded by something.
No, P is always less than 1 over 20.
Right? Oh.
Pn is always for the normality part. Pn is always less than 1 over 20.
Oh, okay.
For the consistency, Pn is just not going to 1. Pn is less than 1 minus kappa. But for the normality, well,
what happened in these examples we learned in the last few days, where you have different scalings depending on what the subgraph is and the graphon is. So why is that not an issue here?
So there is a slight difference between that setup and our setup, right? In that setup, there's an underlying W, which gives you the big graph, which you fully observe. And here our starting point, so essentially the centering is different. Here our starting point is the big graph, and then we further sample a small graph, right? And so the setting is a bit different. So I don't think in Bhaskar setting or in Erdős setting, you'll never get a Poisson limit, if I understand correct. You'll never get a centered Poisson as a limit. Whereas in our case, you can. So it's a bit different. I guess my time is up, but yeah.
Okay, thank you. Okay,